Welcome back to Educator.com and AP Statistics. In this lesson, we're going to talk about correlation and regression. So, an overview of what we'll talk about in this lesson. We'll go over scatter plots. We'll talk about correlation and some measures for actually saying this is how strong the correlation is. We'll talk about what a least squares regression line is and how to interpret the parts of it. And then lastly, we'll do some residual plots and talk about what they mean. And then, of course, we'll do lots of practice. So let's start with scatter plots. So you've probably seen a plot like this before, but the key thing to note about this is that there are two variables, two, in fact, continuous variables, right? So we have two numerical variables, and each dot will have a value for both of the variables. So in this example, we have grip strength and arm strength, and every person can have a measure of the grip strength and then the arm strength. In this case, grip strength is our x variable and arm strength is our y variable. So our x variable is what we call the explanatory variable, and it will explain the response variable. Not letting me write on the edge. It will explain the response variable. So in this case, they're saying that grip strength should be able to explain arm strength. So that if you measured someone's grip strength, you could predict their arm strength. And in fact, if you look at this graph, it does appear that those with larger grip strength also have larger arm strength. Let's look at this other scatter plot. So we have some process and some characteristic. And as the process input goes up, the characteristic goes down. So in this case, with the arm strength and grip strength, there's a positive relationship. As the explanatory variable goes up, the response variable goes up. In this case, there's a negative relationship. As the process input goes up, the as the process input goes up, the quality characteristic goes down. Let's talk more about that. So when you have a scatter plot, you're often going to be asked to interpret it. And whenever you're asked to interpret a scatter plot, that means you're asked for the direction, the form, and the strength. So the direction's pretty easy, right? It's just going to be positive or it's going to be negative. So it's positive if as one moves up, the other moves up, and it's negative if they move in opposite directions, right? So as one moves up, the other moves down. Form. So positive versus negative. Form, this is going to be linear or nonlinear. And linear just means that all the dots are following a pretty much straight line. So in this case, both of these have a linear form. An example of a scatter plot that doesn't have a linear form would look something, right, like this, where maybe it went up and then it went back down again. So that's an extreme example. But in both of these cases, you have linear forms. And for AP statistics, most of what you see will be linear. And then strength. So strength means how close are these dots to a line that goes through it. So if we have a best fit line, how strong or how close are these dots to that line? And that tells you how strong it is. And we can say that it's weak, it's a moderate, or it's a strong relationship. And we'll talk about a measure of that in just a second. So remember, we want strength, it's positive, we want direction, it's positive or negative. We want form, it's linear or nonlinear. And then we want strength, it's weak, moderate, or strong. Okay, so here's an example. Describe the direction, form, and strength of the relationship between the scatter plot. Or they might just say, describe the association. Okay, so let's start with direction. So we see that as horsepower of this vehicle goes up, the weight in tons also goes up. So that means we have a positive, write it out in words, positive, and then form. Do we have linear, or are these dots kind of curving around a straight line? Well, they look like they're making a pretty straight line, so we'll say we have a positive, linear, strength. How close are these dots to a straight line? Well, they're all falling pretty close to this line. If we had some that were like way out here, we might say it's more moderate. But these fall pretty close to the straight line. So we'll say we have a positive, linear, strong relationship between horsepower, which is our explanatory variable, and weight, which is our response variable. Perfect. Okay, so before we've had a strength, but we just said, it's moderate, it's strong, I don't know, we're just kind of picking. Now we're going to put an actual value to figure out, okay, this is what we say is strong, this is what we say is moderate. So the value that we calculate to figure out exactly how strong the relationship is called the correlation coefficient, and R is what we use to stand for the correlation coefficient. So R can be between 1 and -1, inclusive. So 0, right, would mean there's no correlation. So if you have 0, there's no correlation. If you have -1, it's a perfect negative correlation, right? As x goes up, y goes down. If you have +1, well, then it's a perfect positive correlation. So basically, as close as R, the closer R gets to 1, whether it's positive or negative, the stronger that correlation. Once it's at 0, there's no correlation. If we're at 8, so either -8 or 0.8, then we'll say it's a pretty high correlation or a really strong correlation. And then the negative sign, so negative or positive, is telling you the direction of the correlation. So just knowing R, you can already know two things, right? You can know the strength and you can know the direction, but you can't know the form, right? Because R could be low if it's a non-linear relationship. So, right, if we had something that looked like that, well, it's going to have a really low R, so it's going to have a pretty weak linear correlation, but a pretty perfect nonlinear correlation. Does that make sense? So R is only going to be used, we can only use this, only used for linear relationships. Right? Because in this case that I just drew, that would probably have an R of something close to 0. But really, there's a really strong pattern between x and y in this example. So just note, they sometimes try to trick you that R, you're only going to use that to describe linear relationships. But it is very useful because you can get it from a list of numbers and then you can definitively say, I have high, or I have low, or I have somewhere in between. You can put a number to how strong that relationship is. Okay, so let's do an example. What is the approximate correlation coefficient, which remember is our R, between horsepower and weight of vehicle? Okay, so we want to kind of draw ourselves a little line, kind of a best fit line, and say how close are the dots to this line. So if we go back to our little picture, right, we know it's a positive, so it's probably going to be somewhere between 0.8 and 0.3, right, because it's a little bit closer than that, but it's not quite as close as that one. So I would say that this R is probably, and it's definitely positive, right, but it's probably close to around 0.5 or 0.6. So we can say 0.5. And you would never get a multiple choice question where they'd have 0.5, 0.55, and you just have to eyeball it, because you can't know that precisely from just looking. But it's important to note that it will be positive because as horsepower goes up, weight goes up. So let's interpret this correlation coefficient. So what this correlation coefficient means, right, positive 0.5, is that there is a positive moderate relationship, and maybe we'd even say positive moderate linear relationship between horsepower and weight. Okay, so now let's talk about the least squares regression line. So I've been drawing this kind of line through the scatter plots, but there's a much more precise line that can be drawn mathematically. And that line is called the least squares regression line. So a regression line is a line that describes how y changes as x changes, right? How your response variable changes as your explanatory variable changes. Now it's really powerful because it can be used to predict the value of y for any value of x. And there's a caveat to that. but we'll get to that in just a second. But for the most part, we can use it to predict y when we have x. Now, it's called the least squares regression line because if you note, right, we have all of these dots, and this best fit line is calculated so that it makes the square of the distance between each dot and the line, right, so the sum of all those little squares as small as possible. So if you just drew a best fit line between the line or between the dots like I did before, that's not going to be the least squares regression line because it is not precise enough to have made the sum of all of the squared distance between the dots and the line as small as possible. So that's why we're going to have to get our calculator to help us out. Okay, so let's talk a little bit more about the least squares regression line. So the least squares regression line is y hat, and the reason that this is y hat is because it's the predicted value of y, or of your response variable. And then we have a, which is your y-intercept. And then you have b, which is your slope. And then you have x, which is your actual value of x. So that means that for every actual value of x, we can use the slope and the y-intercept of the line and calculate a predicted value of y. Perfect. So we'll use the calculator to get most of these things, but sometimes you do have to calculate them by hand. So in order to calculate the slope, you need to have the correlation coefficient, which is r, and then you need the standard deviation of y divided by the standard deviation of x. So then once you have your slope, you can plug it in and solve for your y-intercept. So the reason you can do this is because the least squares regression line always runs through the point that's the mean of x and the mean of y. So we can use that rule or that fact and the fact that we know the mean of y and we know the mean of x and we've calculated the slope to back solve for a, which is your y-intercept. And just a little review, right? If we have our dots, and let's say that I was a computer and I made the least squares regression line, and that's what it looked like. My y-intercept would be here because the y-intercept is the value of y when x equals 0. So in this case, my y-intercept would be 0. If, on the other hand, my least squares regression line, say my dots are here, let's say my least squares regression line looked like that, well then this would be my y-intercept. So it'd probably be something closer to like 2, right? So let's say 1, 2, 3, 4. So in this case, my y-intercept would be 2. When x was 0, y would be 2. So what's the slope? So the slope, oops, let's get a different color. B, which is the slope, is just how much this line goes up for every one that you go over in x. So the way to interpret it is the slope is how much y increases, right? How much we go up in y for every one increase in x. And you should remember this from geometry, that the slope is just the rise over the run. So how much do we rise up in x when we run over 1 in, how much do we rise up in y when we run over 1 in x? So if that's a little confusing, don't worry, we will do an example. Okay, let's do this example. So a certain psychologist counsels people who are getting divorced. A random sample of 5 of her patients provided the following data, where X is the number of years of courtship before marriage and Y is the number of years of marriage before divorce. Okay, so we have X, right? X, which is our explanatory variable, which is the number of years before people get married, and Y, which is our response variable, which is the number of years before they get divorced. Okay, so just so you've heard this before, X is sometimes called the dependent variable, and Y is sometimes, other way around. X is sometimes called the independent variable, and Y is sometimes called the dependent variable. So you'll sometimes hear this as independent and dependent variables, right? Because they're saying that the change in Y depends on X, which is independent. So just so you've heard them all. Okay, so use your calculator to determine the least squares regression line. Perfect. So the calculator is really helpful for doing least squares regression, and when you're doing this on the AP exam, it's perfectly fine to use your calculator. You do want to say that you've used it, but it's fine to use it and not do this stuff by hand. Okay, so, but actually one caveat on that, sometimes you'll get a multiple choice problem where you will have to know how to do it by hand using the equations I gave in the last slide, but for the most part you'll do it on the calculator. So in order to do this, you're going to want to put these numbers into your list. So you should be pretty good at that. So stat enter. You're going to put all of your X values into list 1, and notice that I've already done that. So we have 3, 1, 1.5, 6, and 2. And then you're going to put all of your Y values into list 2. And note that they do need to correspond, right? So this first person has 3 and 10. This next person has 1 and 3. So you need to make sure that they're lined up. Okay, so now we quit out of here. You're going to go to Stat. You're going to go over to Calc. And then we know that this is least squares regression, which is also called linear regression. So we'll go to linreg. But remember that our linear regression equation was a plus bx, and this is ax plus b. So we're not going to use this first one. We're going to keep going down until we get linreg a plus bx. And then you'll hit enter. Then you'll tell it that you have your x's in list 1, comma, your y's are in list 2, and then enter. And here you go. You have all your values for the least squares regression line. So you know it's y equals a plus bx. A is 5.09 and B is 1.67. So we can say that y hat, and it has to wear a hat because it's just a predicted value, y hat equals A, which is 5.09, plus B, which is 1.67 times X. And then you'll want to make sure that if you're writing X's and Y's, you want to define what they are. So you'll say X equals the number of years before marriage, and Y is the number of years before divorce. Perfect. So now you'll interpret the slope and the y-intercept of the regression line in the context of this problem. Okay, so let's just remember that a slope is rise over run. So it's easy to think about your slope as being 1.67 over 1. So what that means is our run is 1 and our rise is 1.67. So for every 1 that we run over in the x direction, we rise by 1.67 in the y direction. So what that means in the context of the problem is that for every 1 year increase in the number, let's say in the years of courtship before marriage, the number of years before divorce increases by 1.67. Perfect. So now let's look at the y-intercept, 5.09. So what that is saying, right, if we were to draw our regression line, is that our line passes here at 5.09. So when x is when x is 0, y is 5.09. So it's really common that the y-intercept, you'll be asked to interpret it, but it doesn't really make sense, right? So what it's saying is when x, or the number of years before marriage, is 0, then the number of years before divorce is 5.09. So that could make sense if you get married right away, right? There's no courtship before marriage, then they expect to be married for 5.09 years, according to this regression equation, which is made up, so don't take it to heart. Okay? Perfect. So now, interpret the correlation in the context of this problem. Okay, so let's pull up our calculator. You'll notice that I do not have the correlation here, and you may or may not, depending on if you're using a calculator that you got from someone else or that you've purchased brand new. So if it's brand new, then you have to turn on the function to get R. So you only have to do it once, but you do have to do it. So in order to do that, you want to go to catalog. So you're going to go second catalog, so second 0, and then you're going to scroll down to diagnostics on. So scrolling down to D. So we have diagnostics on, hit enter, then hit enter again. So once you've done that, you won't ever have to do it again. So let's go back to stat, calc, and we're going to go to our linreg. So here it is, enter, telling it that it's in, the x's are in list 1, the y's are in list 2, and then when I hit enter, I now have these extra things. So you won't have to do that again, even after you've turned your calculator on and off, but if you ever get a new calculator, you will need to do that. So now we see that our R is 0.6, we'll round to 0.65. So R equals 0.65, which means that there's a positive, right, because it's positive, there's a positive moderate relationship. We have a positive, moderate, or that could almost be strong, so moderate to strong. Relationship between the number of years before marriage and the number of years before divorce. So I just want to point out one thing. This was 0.65, and it's like, well, what's the cutoff between moderate and strong? Well, it really depends on the subject. So if you were doing a physics experiment and you got an R of 0.65, well, that would be a really low correlation, or really low correlation coefficient, because things like physics and dynamics, they're going to be really well correlated. But human nature isn't that precise. So things like years of courtship and marriage and anything that has to do with psychology, 0.65 is actually a pretty strong relationship. So if it has to do with human nature, lower is considered a strong relationship versus if it's math and physics type relationship, we need to see a higher correlation coefficient before we say that it's a strong relationship. But for AP statistics, you aren't expected to know it to that detail, just kind of like, yeah, moderate to strong. You should know the difference between weak, moderate / strong, and really strong perfect. Okay? Okay, so let's move on to the next thing. So notice that when I did my linear regression, I got A, B, R, and then I also got this R² value. So let's talk about what it is. So the R² is the coefficient of determination. And notice that it is literally the square of your correlation coefficient. So if we take our correlation coefficient and we square it, that gets our coefficient of determination. But it's generally always written with a capital R. So the coefficient of determination is going to tell you the percent of the change in Y that is explained by the, and I'm going to underline this because there's two ways to say it. So you can say the percent of the change in y that's explained by the change in x, and then it can also be said as the percent of the change in y that can be explained by the least squares regression line. Regression line. So you'll see it either way, and this is a really common multiple choice question where they'll say, what's the percent of the change in y that can be explained by, and they'll say one of these two things. And all they're asking for is r squared. So notice that you get r squared in your calculator, if I can bring my calculator up, but it's not given as a percent, so you do have to write it as a percent. So for our example, it's 0.419, so it's 0.419, which means that we can say that 41.9% of the change in y, so the change in years before divorced, can be explained by the years of courtship before marriage. Okay, so let's move on to our next little part, which is residuals. So a residual, another way to think about a residual is to just think of it as the error. So it's the error between each point and the predicted point. So a residual is your observed y minus your predicted y. And that's partly why we have this little hat on y, because if we didn't, how would we know which is our observed and which is our predicted? So y minus y hat gives you your residual. Your residual is not r, because we already have a correlation coefficient. So a lot of times we'll just abbreviate residual as resid. Okay, so really quickly, if we have our scatter plot, and let's say we have these few dots, and we have our least squares regression line, so our residual is going to be the distance between our dots and our regression line. So we can use that to get what's called a residual plot. And the residual plot is just going to be the values of x on the x-axis, but then the residuals on the y-axis. And remember that the residuals are just your actual y minus predicted y. So there'll always be a line here at 0. And the key thing about a residual plot is that you want to see no pattern. So if you see a pattern, that's bad. Here, they're just randomly dotted all around, so that's good. It's a good residual plot. So if we see no pattern, what that means is that it's a linear relationship. Linear So if we see no pattern, for the most part, we can say that's a linear relationship. So this least squares regression line that we've created is a good fit for the relationship between x and y. So linear relationship, so our least squares regression line is a good fit. And we'll talk about a lot more about residual plots in a much later lesson, but for now, it's a good introduction. Okay, so let's do an example. A regression of the amount of calories in a serving of breakfast cereal versus the amount of fat gave the following results. Okay, so remember this should always have a hat on it. So we have hat calories, so predicted number of calories is 95 plus 12 times the amount of fat. So this is our y-intercept, and this is our slope. And so remember, what this is saying is that for every 1 gram increase in fat, the calories go up by 12. And for a cereal that has 0 fat, it will have 95 calories. Okay, so you got to know what the slope and y-intercept is. So now let's actually answer our question. A cereal has 10 grams of fat and 200 calories. What is the residual for this cereal? Okay, so know that the residual is y minus y hat. So y is your actual y value. And remember that y is going to be calories. right? Because we know our regression equation is y equals a plus bx. And we know that x is the amount of fat. So our actual number of calories, or our actual y, is 200. So now we just need to know what y hat is. Well, we already have an equation for y hat, so we'll plug it in. So y hat is just going to equal a plus bx. So it's going to equal 95 plus 12 times, in this case, our x is 10. So here we go. Move that over. So we have 12 times 10, so 120. 12 times 10 plus 95. So our predicted y is 215. So that means our residual is just 200 minus 215. So our residual is negative 15. So negative 15 just means that we over-predicted by 15. If it had been positive 15, it would have meant that we under-predicted by 15. Does that make sense? So our actual minus predicted gets our residual. It tells us how big of an error we're off in our prediction. Okay, so let's do another example. So we've already seen this scenario, right? Courtship, marriage. Now we're going to create a residual plot. Okay, so in order to create a residual plot, we need to have our y hats for each data point. So let's go ahead and pull up our calculator, and we'll get our least squares regression line again. So calculate, going down to lin reg. My x's are still in list 1, and my y's are still in list 2. So here we go. I have my regression equation, 5.09 and 1.67. So y hat equals 5.09 plus 1.67x. And we know we've defined x and we've defined y, and you would need to define it, but we already have in the other problem, so we'll say we've already defined it. So now we're going to go through and try to figure out what each of our y hats is. So the easiest way to do this is to go back to your lists. So we'll say stat, enter. So we have all of our x's in list 1, all of our y's are in list 2. So let's put all of our y hats in list 3. So we'll highlight list 3, and remember that we can do any equation on all of the numbers as long as we have list 3 highlighted. So we'll say that y hat is 5.09 plus, and I'll put this in brackets, 1.67, which is my slope, times my x's, and remember that my x's are in list 1. So there we go. We have all of our residuals. So let's just make a little note here that we put our x's are all in list 1, our y's are all in list 2, and our y hats are all in list 3. So I'm going to move this over and write them down. We have 10.1, 6.76, 7.5, let's say 7.60, 15.11, and 8.43. So those are all our y hats. Now we want to get all of our residuals. So write it down here. Our residuals, remember, are y minus y hat. So we'll go over here to list 4, and we know that all of our y's are in list 2. So list 2, and all of our y hats are in list 3. So list 2 minus list 3, and now we have all of our residuals. So we have, I'll write it down, we have negative 1, negative 3.76, 6.4, negative 0.11, and negative 2.43. Great, so we have all of our residuals. Now we're going to make a residual plot. So if you look back, right, at my example of what a residual plot is, maybe, you see that it's just a scatter plot of x's and y's. So we just have to be able to create a scatter plot. Okay, so we're going to go to stat plot. So second, stat plot. We're going to make sure we turn it on. And then this very first picture is a scatter plot. So let's first look at the scatter plot of our two variables, right, of years of courtship and years before divorce. So all of our x's are in list 1, all of our y's are in list 2, and we can say zoom stat. And here's what our scatter plot looks like. So we don't have very many numbers, so it's not like a great plot, but it looks kind of linear. Now let's go back and make this a residual plot. So we'll go second, stat plot, enter. And now, instead of having the y's, like the things on the y-axis being our actual y values, we'll turn it into our residuals. So remember our residuals we had in list 4, which should have written down here, right? This was list 4. So we'll change that to list 4, and then zoom, and then we can scroll down, or we can just press 9. And here we go. We have all of our residuals. So this is a kind of hard residual plot to interpret because we really only have 5 data points, which isn't enough to do regression with, but we are in this example problem because I don't want to have to keep typing hundreds of numbers while you watch me. Okay, so here's our residual plot. All we want to know is that there's no pattern. And with this few numbers, I would say there is no pattern. So we would say there is no pattern in the residuals. So the least squares regression line is a good fit. And then, just so you know, what would a pattern in a residual plot look like? So it's going to usually look something like this. Either they'll kind of fan out, right? Which means that we used to have really good prediction when things are low, and then it starts to fan out. So our prediction gets a little bit worse as we go along. Another way that it might look is like this. Right? So what that means is that in the beginning, we overpredicted, and then we underpredicted, and then we overpredicted, right? Because remember, a negative residual value means we overpredicted. So we don't want that either. You don't want to have a pattern in your error, right? So this is just saying there's a pattern in our error. So we can either have it fanning out or making a curve. That's the kind of pattern we do not want to see. Okay, so let's do another example. At summer school, one of Sarah's teachers told her you can determine air temperature from the number of cricket chirps. Okay, so what is the explanatory variable and what is the response variable? So this is kind of a trick question, right? Because what you think should be the explanatory variable isn't. So you have to get good at reading the story and not just jumping to conclusions of, oh, well, this is what should predict that, but what does it actually say in the problem they're trying to predict? So they're saying you can determine the air temperature from the number of cricket chirps. So you're predicting the air temperature, which means that y, or your response variable, is going to be the air temperature. And x, or your explanatory, your independent variable, is going to be cricket chirps. So this is the response, also known as the dependent variable. And then this is your explanatory variable, also known as the independent variable. Perfect. Okay, so now we want to determine to determine a formula, Sarah collected data on temperature and number of chirps per minute on 14 occasions. She entered the data into her calculator and did 2 var stats, something we'll talk about in a second. Here are some results. Okay, so remember that I did give you equations for calculating the regression line. So you do have to be able to do it using the equations because every once in a while you will not be given raw data. You'll just be given means and standard deviations, and you'll have to use that to calculate your regression equation. So use this information to find the equation of the least squares regression line. So let's remember, the least squares regression line is y hat equals a plus bx. So you have to start by finding b, because you can't find a until you found b. So remember that b is r, or the correlation coefficient, times the standard deviation of y divided by the standard deviation of x. So in this case, it's just going to be 0.361 times standard deviation of y, 9.23, over standard deviation of x, which is 32. Okay, so we can calculate our b. So we'll plug that into calculator. 9.23 divided by 32 times 0.361. So we have 0.104. 0.104. Okay, so now we have our slope. So now let's find our intercept. So remember that we know the least squares regression line goes through the point that has the mean of x and the mean of y. So that means we can say the mean of x equals a plus b, the mean of y equals a plus b times the mean of x. So let's plug things in. So the mean of y, or y bar, is 76.83, which equals a plus b, which we just calculated, times the mean of x, or x bar. And then all we have to do is solve for a. So we'll say 104, or 0.104, which we have here, times, and that just brings the answer up already, times 165.8. Okay, so we have 76.83 equals a plus 17.26. So we'll subtract 17.26 from both sides. So I'll say minus 17.26, which means that a equals 76.83 minus, and you can always do second and this answer, and it'll bring your answer in. That way you don't have to worry about how many decimal points to put in and not get your estimate off. So we have 59.57. So that means that y hat equals 59.57 plus 0.104 times x, and then we'll make sure that we say that y is, what were we predicting, is the air temperature, and x is the cricket chirps. So you always want to give a little key for what your x and your y is. So I just said, remember that I would mention, so this said they did 2 var stats. So we've done 1 var stats. 2 var stats is just kind of a lazy way. If you have 2 variables, you don't have to do 1 var stats twice. You can just do 2 var stats and tell it the 2 variables. So we still have our marriage data in list 1 and list 2, so let's try it. So second quit, stat, calc. We're going to go down to 2 var stats, and we'll tell it, okay, this is my x variable, this is my y variable, enter. And notice that you have the means and the standard deviations of x, and then if you scroll down, you have the means and the standard deviations of y, and then you have this sum of a product, but you don't need that, right? But if you notice, all it's doing is doing 1 var stats, but twice. So you get to do 2 things with 1 step. So whether or not you want to do that, it's totally up to you. Okay. Oops, I think I skipped a slide real quick. Okay, so one of Sarah's data points was recorded on a particularly hot day, 95 degrees Fahrenheit. She counted 2,432 cricket chirps in 1 minute. What is the residual for this data point? Okay, so remember that the residual is just y minus y hat. So our y is going to be the actual temperature, right? Because remember, y is temperature. So this will be 95 degrees. And then y hat, we're going to have to calculate. So if we look back at our equation, we see that it is 59.57 and 0.104. So all we have to do is plug in our x, or our number of cricket chirps, and get a predicted temperature. So we'll plug 2,432 in here. So let's pull up the calculator. So we have 0.104 times 2,432. And I always do it order of operations, right? I'm going to do my multiplication first, and then I add to it, just so you don't have to worry about brackets. And then plus, and it brings up the answer, 59.57. Enter. So now our predicted temperature was 312.49. So a little too hot. So that means that her prediction is way off. And if you look, it's very possible because she had a really pretty small R-squared, so it wasn't a great prediction variable. Oops. Okay, but let's find the residual anyways. So our residual is going to be 95 minus 312.42, which is, pull up the calculator, minus 95, which is 217. So that's a huge residual. So the reason I did this example with this huge residual is because I want to bring up a really important point. So remember that earlier I said the beauty of a least squares regression and this linear regression stuff is that you can predict a y from any value of x. Well, the truth is that you cannot extrapolate. So we say, do not extrapolate. So what that means is if Sarah had collected data between 0 degrees Fahrenheit and 75 degrees Fahrenheit, sorry, I have her stuff reversed. If her data had been between 0 degrees Fahrenheit and 75 degrees Fahrenheit, and her chirps, say, had been between 100 and 1,000, well, that's the only data range that she can make predictions about. She cannot extrapolate way out here about some crazy big number of chirps because she didn't collect data in that range. So it's really important you cannot extrapolate. If you collect data between 100 and 1,000, don't try to predict something for 2,000. Does that make sense? Okay, so let's do another example. In a statistics course, a linear regression equation was computed to predict the final exam score from the score on the first test. The equation was, this should say final, or actually this should say y hat, sorry about that. The equation was y hat equals 12 plus 0.8x, where y is the final exam score and x is the score on the first test. Sarah scored 95 on the first test. What is the predicted value of her score on the final exam? So this is a really common regression type problem. You're given the equation and they say, here's a value of x, what's the predicted value of y? So you should be able to do that in your sleep. So we'll write it out. We know that y hat is 12 plus 0.8x. And we know that Sarah scored 95 on the first test. So her x was 95. So that means that her y hat, or her predicted score on the second test, was 12 plus 0.8 times 95. Bringing up the calculator. So that means that we predict that on the second test, she will score 0.8 times 95 plus 12, that she'll score an 88. So the second test, I guess, was a little bit harder. So she's going to score, we say that she's going to score 88 on her final. So we'll say that 88 is her predicted, right, wearing a hat, final exam score. Okay, so refer to the previous problem. On the final exam, Sarah actually scored a 96. What is the value of her residual? Okay, so we know that she actually scored a 96, which means that her actual y value is 96. We want to know her residual. And remember that a residual is just y minus y hat. So her y is 96, and her y hat, or her predicted value, we remember from our equation, was 88. So we have 96 minus 88, which means that we underpredicted her score by 8 points. Perfect. So hopefully regression makes lots of sense, and I'll see you in the next lesson.